Okay, so we've talked about ohm, V equals IR. We talked about Kirchhoff's voltage law. Sum of the voltage drops around a closed loop equals 0. We've talked about, in this case here, silicon diode, which has a polarity, but it has a 0.7 voltage drop to it. And we've also talked about voltage divider circuits in a two-resistor circuit, how to calculate the voltage in between the two resistors. Okay, so let's look at what Thevenin was all about. So when you look inside, look at your PC, and you see a port. You plug into the port, there's a voltage there and a current that will come out, but there's also a bit of an internal resistance. You can plug anything into those ports. It doesn't know if, for example, if it's USB, which has power and ground, it doesn't know if it's a mouse, it doesn't know if it's a scanner, it doesn't know what you're plugging in. So effectively, when you look at a circuit, and let's take this circuit here, and here like this, and let's just put another resistor here. All right. Let me use some numbers. Why don't we use like 10 k ohms? 10 k ohms sounds about right. What, 15 k ohms? Yeah, why not? Okay. Now, I need a voltage, 5 volts. All right, so what we do is, in our circuits, we tend to apply a load. And a load is just something that requires current, okay, a load. And these loads can be different. I mean, if it's some kind of a heating device and you keep turning the thermostat, you're going to draw more or less current. So the thing is, what we'd like to know is, really, if this is a black box on this side here, okay, regardless of the load that's applied, at least let me understand what's coming out of my black box. What is the voltage? And what is the internal resistance, which then would drop the voltage as current is pulled. So if we look at this circuit here, the interesting part is the current is only flowing in this loop here, and I'm going to just disconnect the load so we're not confused. I'm just going to disconnect this load, okay? So it's external. So the current is only flowing in this loop here, which means that we have a voltage at this point here. Now, do we have a voltage at this point here? The answer is yes. And the voltage at this point here, okay, let's call it Vx, is going to be the same as the voltage at this point here. No current will flow, but the presence of charge, the presence of the pressure pushing the charge, I can see it from this side of this resistor. And it's like cars driving on a road. Here, unfortunately, there's a huge chasm and nobody's going anywhere, otherwise we'd have a problem. So the electrons, or charge as it be, would just park themselves here, which means that there's no voltage across here. These two are the same. No current flows here, but you do see a voltage here. This concept of an open source voltage sometimes is a bit problematic with new students. Regardless, we know now that we have a current flowing over here, so we have basically, let's use our voltage divider formula here. So V across the 15 k ohms is equal to Vs. Let's use this formula here. It'll be 15 k divided by the sum of those two, 25 k. And Vs in this case here was 5 volts. So we have 5 times 15 times 10 to the 3 divided by 25 times 10 to the 3. Okay, that's 15, 30, 45, 60, 75 divided by that is equal to 3 volts. Okay, so at this point here, Vx is equal to 3 volts, as is equal to here, 3 volts. Now, we're talking about Thevenin. He says, it's one thing to know what is the voltage presented outside of this black box, okay? What is the voltage presented to the load outside of this black box? But internal to the box, there is an internal resistance. And as current is drawn, there will be a voltage drop across the internal resistance. So what he tried to do is create a model of not only the voltage source presented to the load, but also the internal resistance. So how do you figure out what the internal resistance is? Well, essentially, you've got to put your eye over here. So you put your eyeball here. All right, that's you. And you look in to this device, into this circuit. So the first rule we had with Thevenin is disconnect the load, okay? So we disconnect the load. That's the first thing. The second thing we do is we short out voltage sources. Okay, so let's just do that. If that is the case, then we're going to remove this voltage source and replace it with a wire. And as you know, the resistance of this wire, at least the wires we use in the labs, is negligible. Actually, let's use for conversation purposes 0. So we have to short this particular voltage source out, which means we're bringing this resistor, we're bringing it down to this point. We've actually got 2 resistors in parallel. I'm looking in from this side, and 1 resistor in series. So again, R1, R2, R3. We have, well, let me put it here, R1 in parallel with R2, and that is added to R3. Okay, so 10K in parallel with 15K. The first rule is that resistors in parallel, the final value of resistance looking at parallel resistors is less than the smallest resistor there. And I'm going to use a quick formula. I'm going to use R1 times R2 divided by R1 plus R2, which is calculating resistors in parallel, this here, all right? And that's going to be, here we have 150 times 10 to the 3 times 10 to the 3, correct? And we're going to divide that by 25 times 10 to the 3. So that's going to leave us with 6 times 10 to the 3, 6 k ohms. 6 k ohms for the 2 parallel resistors. So this becomes 6 k ohms. And we're adding to that another 10 k ohms. So the total resistance that we're looking at from this side of the circuit into this black box is 16 k ohms. Okay, 16 k ohms. So what Thevenin says is, instead of working your ohms and Kirchhoffs every time you put a load on there, why don't we just simplify this circuit by putting in a battery, in this case here, of source 3 volts, and a series resistor of 16 k ohms for this particular circuit, and then go ahead and attach your load and do your calculations. We've simplified 3 resistors down to 1 in this case here, and we've also simplified the voltage that's present on the circuit that is contributing to then whatever load you add. So again, disconnect the load first in order to determine what is the voltage that you see. If you leave the load connected, you will have a different number here altogether. And then secondly, once you've disconnected the load and determined the voltage, determine the resistance looking into this Thevenin, we call that Thevenin resistance. Determine the Thevenin resistance from shorting the voltage source there.